So this is the ninth session on signals and systems, and from this session we start the study of operations on signals. And in this particular session we will study two operations. Other operations we'll take in the succeeding sessions. In this session we are going to study two operations, mainly one, multiplication by a constant, and multiplying two signals. Understand that a system basically accepts an input or maybe more than one input, although initially we take only one input, and then processes them and generates an output. So this is what we mean by the operations. And in this session we are going to study these two. So alright, so let us start. Multiplication by a constant. So input output equation for this is very simple. Y is equal to k times xt, where xt is the input to the system and y is the output from the system. And just as since we are using the variable t, it means that right now we are talking about a continuous time signal. Later on we'll look at the discrete signal as well, discrete time signal as well. Alright. Now if k is greater than 1, then the operation is amplification. Understand, when we say that k is constant, what we mean is that it's not a function of time, it's constant. It could be 2, 3, 4, 0.5, 0.4, whatever. And if k is greater than 1, then we say that operation is that of amplification. But if it is less than 1, then we say that operation is attenuation. Output is less than the input. Okay, so let's take one example. So I have taken one particular input signal, but this explanation can apply to any kind of input signal. It may be this, it could be a triangular pulse, it could be a square pulse, it could be a periodic signal, and so on. But some example has to be given, so I am starting with this input signal. So what we are going to do now is to show you an output waveform which consists of three parts. One input signal, and one output when k is less than 1, and one output when k is greater than 1. So of course at a time the system will do either this or this, but in one plot we want to show what happens when k is greater than 1 and what happens when k is less than 1. Obviously when k is greater than 1, the output will be greater than the input, and when it is less than 1, it will be less than the input. So let us look at a graph like that. So in this case, this is our input signal. It's looking, its amplitude is looking lesser than this only because scale is different. Note that this is from 0 to 2, whereas this is from 0 to 1. So this is my input. This yellow line diagram that you see is the input signal, that is your xt. Then this blue waveform that you see corresponds to k equal to 2. So every point in the input signal gets multiplied by 2. For example, here this is 1, so this becomes 2. Here if it is 0.5, then it becomes 1. So this blue waveform tells you that the system is working like an amplifier. On the other hand, if k is less than 1, for example, if k is equal to 0.5, then output is exactly halved. So if the input is 1, here it is 0.5 and so on. So that is how the input and output signals will look like. Now this particular case we have considered continuous time signal, but similar results are applicable for discrete time signals also. So let us just take a look. We'll go through this quickly now. It's completely analogous. The only difference is that instead of t variable we have n, which is a discrete variable, so it will have only integer values. So again the same argument applies. If k is greater than 1, operation is amplification. If it is less than 1, the operation is attenuation. And this is the input signal. Again notice that the x-axis is calibrated in terms of sample index n, which is an integer. So we are assuming that our signal starts from -3 and goes up to 7. And for these -3, -2, -1, the value is 0. Then at 0 it is 0.5, at 1 it is equal to 1, 1, 1, and so on. This is how it looks like. So how the output will look like? Again similar, except that you will have a discrete time line plot. So output signal with k equal to 2. When the input is 1, the output is 2. As you can see, here the input signal is not seen, but we have just seen it, and we know that the maximum value was 1. So in this case it is 2. So similarly, every sample gets multiplied by 2 and you get this. Of course, if 0 is multiplied by any value, it remains 0. And here if you multiply it with k equal to 0.5, then the signal gets attenuated, it gets reduced. Attenuation means reduction. So if the input is 1, it now becomes 0.5 and so on. Okay, so the multiplication by a constant is a simple operation, and we have seen how it works for both continuous time as well as discrete time signals. Let us now see what are the applications of this. Now, in which cases you require amplifier? Now, in electronics field, there are very large number of cases where amplifiers are required. I'll just tell you a couple of them. So, output of a transducer is usually small before it can be used. So, an amplifier is necessary. For example, consider the output of a microphone that may be in the values of say millivolts and so on. Whereas for processing or for display or any other purpose, you will require generally a larger output. So what you are going to do is to amplify this. Also, the output of a thermocouple also has a small value, and it's necessary to amplify it before it can be either processed or it can be used for display. Okay, then what about attenuators? Volume control in sound system. This is a typical example of an attenuator. So there is a certain maximum level of sound, and you can change the position of the attenuator when you want to reduce that sound. Here, of course, we are doing it through a program. Then at the input of a CRO, you must have seen that you have got an attenuator switch. So if you are connecting to the Y input of a CRO, you will be able to control the amplitude that goes to the Y plates. So these are a couple of examples which tell you where amplifiers are required and where attenuators are required. And these are examples of cases where you are multiplying the input signal by a constant. Okay, let's now see one more operation in this session, that is multiplying two signals. So suppose xt is one of the inputs, that is a function of time, and yt is the second input, which is also a function of time. Note that in this particular case, the case is different. So in the previous case, the multiplying factor for the given input signal was a constant. In this case, it's not so. We got two inputs, both of them are functions of time, and we are multiplying them in order to get the output. So zt is the output, xt is one input, yt is second input, and this is what we get. This is the equation defining the system, you can say. Similarly, you can write for the discrete time signals Zn is equal to Xn multiplied by Yn. Now, one important thing to note is that when you are trying to implement this in MATLAB, if you simply use the multiplication sign that of a star, it will not work in this particular case, because every variable in MATLAB is stored as a matrix of numbers, and the multiplication sign denotes matrix multiplication, and that is not what we really want to do. So let me explain that with an example. So what we need is, as I said, is a point-wise multiplication, and let me show an example of this. So suppose you have a sequence of numbers, x is equal to 1, 3, 2, and y has samples which are -1, 5 and 4. So when we say we are multiplying x with y, what are we saying? We are saying that we are generating an array where each element of the array is the product of corresponding elements in x and y. That means the first element in x is multiplied by the first element in y. So 1 into -1, that is the first output, which is -1. Then second, 3 multiplies 5, and I get the second element in the output, that is 15. Finally 2 multiplied by 4, and you get 8 here. So this is what you want. Uh, Incidentally note that in MATLAB, okay, so star cannot be used because this denotes matrix multiplication. That means you want number of columns in the first equal to the number of rows in the second one, which is not true in this case. So they actually, you will get an error message. So I'll come to that. So simple star will not work because the MATLAB will take it as matrix multiplication, and what we really want is point-wise multiplication. So point-wise multiplication in MATLAB can be done by using the symbol point followed by star. This will work. Of course, understand that whenever you are doing these kind of operations on two signals, multiply them, add them, subtract them, divide them pointwise, then it is of course necessary that number of elements in both signals must be same. That is necessary. Otherwise, MATLAB will generate an error. So that is something you should keep in mind whenever you are writing programs for processing. Okay. So let me just show that to you. Suppose in the MATLAB console you enter this x132 y minus 154 and then write z equal to x dot star y, then this is the answer you will get. This is something that we have already discussed. I'm just saying that if you enter this in the MATLAB console, you will be able to show that. All right. Now, if you simply use star, you will get an error message. So suppose you say z equal to x star y, then you will get error using star. It will say incorrect dimensions for matrix multiplication. Check that the number of columns in the first matrix matches the number of rows in the second. So to operate on each element of the matrix individually, use point star for element wise multiplication. So just remember that whenever you want to do point wise operation, you should not use star, you should use point star. So this will apply to multiplication, and it will also apply to division. For addition doesn't matter so much, because if you say x plus y, whether it's a matrix addition or point-wise addition, is going to be same. There is no difference. Okay. Now we want to show a couple of applications of multiplication. So let us look at one. One application of multiplication is in generating a signal called as a modulated signal. And this is called as the process of modulation. Why this is required? This is required because if you want to send low frequency signals by wireless, it's very difficult to do so, because the antenna size required for wireless transmission it depends on the wavelength, and wavelength is inversely proportional to the frequency. So if the frequency is low, you will require enormous size of the antenna, which is never practicable. So what you normally do is you take the low frequency signal like an audio signal or a signal from a transducer, whatever it is, it's a low frequency signal, and then you translate it to high frequency by doing the process of modulation. We shall see how that is done in a moment. But the point is, this is required because a low frequency signal cannot be sent directly by wireless. So modulation is used. So in now modulation, there are a number of types of modulations, but in one type of modulation, amplitude of a carrier signal. Now this carrier signal can have a much higher frequency. It can lie in the radio range where the antenna size becomes practicable. So amplitude of this carrier signal is changed in accordance with the information signal. So what you do is, one parameter of the carrier signal, in this particular case amplitude, you change it in accordance with the information carrying signal. So now the signal that you obtain still has high frequency components, so that you can use a practical sized antenna, but at the receiver side you can simply detect the amplitude variations and you will get your original signal. We'll see that in a short while. So suppose your modulating signal is given by 0.7 sine of 2 pi fmt. Now notice that the modulating signal in an actual system is really going to be an information signal that you want to transmit. It may be sound or it may be data from some transducer. So it's not really a deterministic signal. It is a random signal. But right now, to keep the programming simple and also to explain easily what are the frequency components which are in the output, I am just using sine wave as the input with a frequency FM which is going to be comparatively low. So M is modulating signal. Then you have a carrier signal, that is sine of 2 pi FCT. So FC is much larger than FM. This is your carrier signal. And the output, there are a number of ways in which the output can be obtained. This is one way. So Y is equal to 1 plus M multiplied by XC. So this is 1 plus M into sine of 2 pi FCT essentially. So what you are doing is you are essentially changing the amplitude of the carrier signal in accordance with the modulation signal. Now you add this one for the reason I'll explain in a short while. But one thing you should note that this M is continuously changing with respect to time. Therefore, the amplitude of the carrier signal will also change continuously with respect to time. However, we can easily see what is its maximum value of the amplitude, and what is the minimum value of the amplitude. So this will be, since this is 0.7, clearly the sine wave has a maximum value of 1. So M will have a maximum value of 0.7. That means 1 plus M will have a maximum value of 1.7. And when M is negative, in that case this will be minus 0.7 sine of 2 pi. The maximum negative value will be minus 0.7. So this is 1 minus 0.7, that will be 0.3. So this tells you that the amplitude of the carrier signal in the output, in the input of course it is constant at 1 here. It could be something else, but I have to demonstrate, so I am taking a simple 1 here. So what I am trying to tell you is that the carrier signal itself has a constant amplitude, but when you perform this multiplication 1 plus M into XC, then the amplitude of the carrier signal in the output goes on varying, and this variation depends on the information signal, and that is why you can extract it at the receiver. It will be more easily understood if we look at the waveforms. So let's look at the waveforms. So for convenience, I have given these equations here, and let's look at the waveform. So this is your modulating signal, which is M, and this is a sine wave of low frequency. For convenience, please remember, understand that this is actually an information carrying signal. So strictly speaking, it will be a random signal, but its frequency components will be restricted to audio or whatever application you are using. But for simplicity, right now we are considering modulating signal as the sine wave. And since we took it at 100 Hertz, note that one time period takes 0.01 seconds. The x-axis is calibrated in terms of time. And in this particular case, as we shall see when we look at the program, carrier signal is 10 times this signal. So during this time period, you got 10 cycles. In actual practice, the radio frequency signal is actually much higher than the modulating frequencies. The carrier frequency is generally very, very high compared to the modulating signal frequency. But in order to make the nature of the carrier signal clear to you, I have used a carrier frequency which is only 10 times the modulating signal. Otherwise, you will hardly see anything here. Okay. And then when you perform this multiplication, this is the output that you will see. So this red line is not strictly a part of the output. The blue lines basically define the output waveform completely. However, this red line is drawn specifically to explain to you that the information carrying signal is present in the modulated signal, and that can be extracted. So you might have studied in 12th that you can use a peak detector in order to sort of detect this signal, remove the DC component, and the receiver will recover the original modulating signal. Okay. Incidentally, note that this is going to be a high frequency carrier. What about the frequency components of the modulated signal? Since you are multiplying these two, note that M is a sine wave, XC is also a sine wave. So when you multiply the two, and the one is already there, so the output frequency components will be one carrier frequency, and the other will be FC plus FM and FC minus FM, because product of sine into sine gives rise to sum of frequencies and difference of frequencies also. So all these frequencies really have a fairly high value. So this signal can be transmitted by wireless, and at the receiver it can be demodulated by simply using a peak detector. All right. The point was to show to you that multiplication of the two signals has an application in communication systems where you generate a modulated signal by using a multiplier. Okay. What about the program? So this is as usual our first line. Then FM, modulating signal frequency is 100 Hertz. FC, as I said, we are taking only 10 times larger. So T, that is the time period of the modulating signal, is 1 by FM. We require this T because we want to plot certain number of cycles. So if I say 4T, I'll plot 4 number of cycles. If I say 3T, I'll plot 3 number of cycles, and so on later on in the time vector. So A equal to 1, that is the amplitude of the carrier. Now Fs, this is, remember, we are basically doing a continuous time simulation. So you require a sampling frequency which is very large compared with this. So I have taken 1000 times large. This is 1000, this is 10 raised to 6. So the sampling time itself is equal to 1 by Fs. Now you generate your time vector 0, Ts, 4 times T. So I will see 4 cycles of the modulating signal. Then M is again 0.7 sine of 2 pi FMT as discussed. XC, this is A sine of 2 pi FCT, but A is equal to 1 as defined here. Then you generate your Y. So that is 1 plus M. Now note this, dot star multiplied by XC. And now you want to plot all these waveforms. So you want to plot M as a function of time, you want to plot XC as a function of time, and you want to plot Y as a function of time. So all that can be done now. So since you want 3 plots in the same window, what we do is we use a command called as a subplot 311. If you look at these 3 parameters, what they mean is, if you multiply first by the second, that will tell you the number of graphs you will generate in one window. So 3 into 1, we want 3 graphs. But what 3 means? It means it will generate in 3 rows and 1 column. So you'll get 1 graph here, 1 below that, 1 below that. So column will be 1, but rows will be 3. But you can change this also to get a slightly different picture. But we are using 3, 1. And now this 1 means the first plot. So what is that first plot? Plot T comma M. So we are plotting the modulating signal. Then you say grid on, title modulating signal, sub. Then so once this is done, then you say subplot 312, second plot. So that is the carrier signal, grid on. Then subplot 313, that is the modulated signal. Then we say hold on, just to plot 1 plus M. And reason for that is that red waveform, you remember, we wanted to show that the amplitude is changing as per the modulating signal. So we show that. So when you execute that, this is what you will get. So we have already discussed this, but this is the output that is generated by the MATLAB program. All right. So this is one application of the multiplication operation. Second application is in a musical note generation. This involves generating 2 signals. What are they? Periodic signal of appropriate frequency, that is basically my tone signal, and an envelope signal, ADSR, attack, decay, sustain, and release. And note is generated by the product of the two. So what I'll do is, instead of going through the explanation once again, I'll just refer you to the 6th lecture on music through MATLAB. If you listen to this lecture, you will understand how the ADSR is generated. Understand this is an envelope signal. See, for example, suppose you consider that on sitar someone plucks a string. When he plucks a string, the volume of sound immediately jumps up and then slowly dies down. So that is called as an envelope. And the actual note that is generated by the vibration of the sitar is a periodic signal of appropriate frequency. It depends on which fret you are pressing and all that. Anyway, so if you go through this reference, you will understand this in more detail. Right now, I'll just show you the waveforms. So this is a waveform corresponding to the note. Since the note time period is much smaller than the ADSR, I have used a smaller total time range here, otherwise you will not be able to see the waveform. And this is your ADSR, attack, decay, sustain and release. And when you take the product of the two, this is what you get. So this gives you another application of the multiplication operation, and that's all in this session.